Hi guys, hope you all are doing good. So in this lecture, we are going to learn one of the most important topics in design and analysis of algorithms. The topics are asymptotic analysis, time and space complexity, and best, worst, and average cases, and growth of function. So do not worry if this word sounds difficult. By the end of this lecture, you will understand everything in a very simple way. So without any delay, let's begin. So first, we're gonna see what is an asymptotic notations. Asymptotic analysis. So imagine you have two students. Let me suppose you have two students. So first student name is A and second student name is B. So suppose if student A solves a math problem in 1 minute and the same problem has solved by B, student B, in 5 minutes. So now the question is, which students solve this question very fast? Who is faster? So obviously student A. In the same way, when we have two algorithms, we need a way to compare them. Asymptotic analysis helps us compare algorithms based on how they perform when the input becomes very large. So let me write the simple definition of asymptotic notation. So asymptotic analysis is a method of is used so asymptotic analysis is a method used to measure efficiency of an algorithm. So it tells us how much time an algorithm takes and how much memory an algorithm uses. So now we're gonna see what is time complexity. So let me write what is time complexity. So time complexity. So time complexity means it tells us how the running time of an algorithm increases when input size increases. So input size is represented with n. So it is represent input size. Input size. So for example, suppose you have a list of five numbers. You check every number one by one. For example, for five numbers, you perform five checks. For five list, you perform five checks. Suppose if there are 10 numbers, you you will do 10 checks. So like that, if there are 100 numbers, you perform 100 checks. The number of operations grows with n. So the time complexity is represented with O in brackets of n. This should be read order of n or big O of n. So let me tell a simple example of time complexity. Suppose if there you need to print numbers from 1 to n. Suppose n equal to 5. So we're gonna print up to 1, 2, 3, 4, 5. So the loop learns 5 times. If suppose n equal to 100, so you're gonna print 1, 2, 3, and so on up to 100. So the loop runs 100 times. So therefore the time complexity will be, means TC means time complexity will be big O of n. So because the number of operation grows directly with n, so now we're gonna see what is space complexity. So now we're gonna see about space complexity. So space complexity tells us how much memory an algorithm uses. So memory means storage inside the computer. For example, you store 10 numbers. Suppose you need to store 10 numbers. So you need a memory for 10 numbers. Suppose you store 100 numbers means you need more memory. Therefore, memory usage increases with input size. So this is called space complexity. So this is the definition for space complexity. It tells us how much memory an algorithm uses. So it is the amount of memory required by an algorithm. So let me write an example for space complexity. Suppose we store n numbers inside an array. Suppose let the size will be n. So you store n numbers. Suppose the n equal to 10. So the memory of 10 numbers, so it will allocate memory for 10 numbers. Suppose if the memory n equal to 100, it allocates memory for 100 numbers. Therefore, the space complexity equal to big O of n. So because memory grows with n. So now we're going to see what are best cases, worst cases, and average cases. First, we're going to see best case. So best case means the most favorable situation for an algorithm. So let me give an example. Suppose imagine searching for a number. Suppose you are searching a number. The list is 10, 20, 30, 40, and 50. So search for 10. So the number will be is found immediate. Number is found immediate because 10 is located at 0 index. Only one comparison is needed. This is the best case. So that time complexity will be big O of 1. Suppose this is the constant time because only one operation is required. So now we're gonna see about worst case. Let me move to the next page. So worst case means the most difficult situation for an algorithm. So let us take a previous example. That list is 10, 20, 30, 40, and 50. Suppose you want to search for 50. So the algorithm checks 10, 20, 30, 40, and 50. So we have found our element. So it checks every element. So that time complexity will be big O of n, means it's searching every number. So this is the worst case. We have took 5 checks, but in our previous example means for best case we have taken only one. So that is called best case. So we have taken long time. So this is called worst case. So now let us see about average case. So now we're gonna see about average case. So average case means the normal situation. Sometimes the element is found earlier, sometimes it is found late. So we calculate the average amount of work performed. This is called average case. So let me write a simple definition for average case. So average case means it represents the expected performance of an algorithm. So this is the average case, best case, and worst case. So now we're going to discuss about the growth of functions. So growth of function means it tells us how fast an algorithm grows when input size increases. Suppose n becomes larger and larger, different algorithms grow at different speeds. So let us see them. So first one is big O of 1. So means it is constant time. The best case, constant time. So, for example, accessing the first element of an array, no matter if array has 10 elements, 100 elements, 1000 elements, and infinite elements, the work remains the same. Growth is very fast. So, fastest complexity. So, this is the fastest one. So, now we're gonna see about big O of log n. It is called logarithmic time. Logarithmic time. So, for example, binary search. So, instead of checking every element, we divide the search phase into half again and again. For one, for example, suppose if we have elements like we have 1024 elements, only about 10 steps are needed. It is very efficient. I had made a complete video on binary search. You can check it out in the I button. So this is very efficient. Now we're gonna see about. So let me erase this. So now we're gonna see about big O of n. It is linear time. So example, traversing an array. If input doubles, work also doubles. So it is good performance. So now we're gonna see about I mean big O of n log n. So for example, met slot. So quick slot is average and faster than big O of n square, used in many real world applications. So now we're gonna see about big O of n square. So this is called quadratic time. Quadratic time. So for example, nested loops. For every element, we check all other elements. If n increases, operation increases very rapidly. So not situation for very large inputs. So let me write an table of comparing these all growth of functions. Let me draw a table. So this is the table of growth of functions. So big O of 1 is the best case, and big O of log n is the excellent case, and big O of n is somewhat good case. So big O of n log n is efficient, and big O of n square is slow, and big O of 2 power n is very slow, and big O of n factor is extremely slow. As all programmers, we always try to design algorithms with smaller complexity. So let me give a real life example. Suppose imagine delivering parcels. So algorithm A visits every house one by one. So when it compares to algorithm B, uses a small map and shortest route. Both reaches the destination, but algorithm B is faster. So this is why algorithms are very efficient matters. So I hope this lecture is clear to everyone. If you have any doubts, you can ask in the comment section. So thanks for watching and see you guys in the next lecture.